let's talk about electron configurations of ions. We mentioned this a little bit earlier. Anions form when atoms gain electrons, so we're adding electrons. And cations form when we lose electrons, so we're taking electrons away. So for the main group elements, things just always make more sense in the main group, and the transition metals are the weirdos. So in the main group, we're just going to remove any electrons in reverse order of filling. So if we have the aluminum atom and we want to know the electron configuration for the aluminum ion, we need to remove 3 electrons. So we'll go from the end, we'll take off the 3p1 and 3s2. That's 3 electrons removed, and so we end up with this electron configuration, which is the same as neon. In the transition metals, we can't just do reverse order of filling. We have to remove the valence electrons first. So for iron, this is the electron configuration. And what are the valence electrons? They are the ones with the highest number here. So there are 2 electrons staying on the 4th floor of the hotel, even though the 3rd floor is not completely full yet. But those are the valence electrons. So as iron loses electrons, it's going to lose those first. Because if a tornado comes by, it's going to take the top floors off the hotel first, right? It's not going to snatch people out of a room on the next lower floor. It's going to take the top floors off first. So you're going to lose the 4s electrons first. If you need to lose more, then you can go into reverse order of filling. So for an Fe2 plus ion, having lost 2 electrons, we're going to lose those 2 valence electrons. And we're going to get this as the electron configuration. If we're going to go to the Fe3 plus, we need to lose 1 more electron. Now we can go here to the 3d6 and take one of those off, and we end up with 3d5.
So how do we know, like, the valence electrons for the transition metal? Because I know, like, when we're writing it down, it's given to us from what's behind it, but how do we know that in this case specifically?
Well, so except for copper and chromium, we can just sort of generally say that all of the transition elements are going to have 2 valence electrons in that S room on the next higher floor. So they're going to lose those 2 first, and if they lose more, then they'll dig into the d orbital.
Okay.
Yeah. So looking at the the orbital diagram here, and we see that this room is actually completely empty, and this 3D room is half full. And that's not the order in which it filled up, because this room is cheaper to stay in than the 3D room, and so the electrons go in there first, and then they fill in here. But when they're leaving, we're not going on price, we're going on what floor of the hotel is the tornado taking off. Can you tell I grew up in the Midwest? Just take stuff off the top of your place. You can't do it with earthquakes because the whole thing would probably fall down. Okay, so any questions about electron configurations for cations? The anions are you just add electrons, and it's a lot easier. So this is where we're concerned about paired and unpaired electrons, magnetic properties. So an atom or an ion will be paramagnetic if it has unpaired electrons. That means it will be attracted to a magnetic field. And that's because an unpaired electron will generate a magnetic field due to a spin. And you could think of the paired electrons as the 2 opposite spins sort of canceling it out, and so they don't generate a magnetic field. Diamagnetic, all the electrons are paired up, and these atoms will be slightly repelled by a magnetic field. So we have paramagnetic and diamagnetic, and this can be confusing. So we got the prefix para and the prefix di. And para, unfortunately, sounds a lot like pair, right? But it's not. Di definitely means two, right? So how did the animals enter Noah's Ark? 2 by 2. So diamagnetic, 2 by 2, all paired up. And that leaves this one to have some unpaired electrons. Diamagnetic, 2 by 2, the electrons are all 2 by 2, they're all paired up. Paramagnetic, there's at least one that's unpaired. Which one's attracted to the magnetic field? The one that has that at least one lonely electron spinning, that generates a magnetic field. The paired up electrons are going to cancel each other out, and so they're not going to generate a magnetic field. So write the electron configuration and orbital diagram for each ion, predict whether they're paramagnetic or diamagnetic. So here we'll get some practice with two different things. So here's cobalt. So we're just going to do what's after the noble gas, right? So cobalt would be argon. And we're going to look at the electron configuration for the atom first. So argon, and then what comes after argon? You go over there, and we're on row 4, right? And the first two columns represent 4s, right? So that would be 4s2. And then the next part, that's where it sank down. This is the D level, and it's 3D, right? So there's scandium, titanium, vanadium, chromium, magnesium, iron, cobalt. 1, 2, 3, 4, 5, 6, 7, right? So we go over 7, 3D, 7. Okay, so we can't tell just by looking at the electron configuration if everything's paired up or not. If you think hard, you can, but we don't want to think very hard, do we? No, we don't. So let's look at those electrons, right? So there's 2 over here. That's the 4s, and then this is 3d. And there was 7, right? 1, 2, 3, 4, 5, 6, 7. That's the atom, right? Is a cobalt atom paramagnetic? Diamagnetic means they're all paired up, 2 by 2 by 2. It's not diamagnetic, so this atom is paramagnetic. What about the ion? Well, what electrons are we going to lose first? It needs to lose 2 electrons. We're going to lose these 4s electrons because those guys are staying on a higher floor, and the tornado takes off the 4th floor before it takes off the 3rd floor. So we're going to get rid of those guys. We're getting rid of these guys right here. So is this ion paramagnetic or diamagnetic? Paramagnetic. The electrons are not all paired up. 2 by 2 by 2? No.
So like would we need to rewrite it like argon, radium, 7, all of that, or not necessary?
Like if this was a worksheet problem and you just cross that off, I'd be fine with that. Yeah. So let's look at the nitride ion. Again, let's start with the nitrogen atom. So nitrogen would be helium, and then we're reading this off the periodic table. We go over to row 2, and we've got the S block, so 2s, 2, and then we're into 2p, and nitrogen is 3 boxes in, right? So that's the nitrogen atom. And we can look at the orbital diagram for that. It's going to fill in like this. The nitrogen atom is paramagnetic, right? To make this ion, we have to add 3 electrons. So I'm going to add 3 electrons to this. They're going to go 1, 2, 3. So that's going to make this a 6. Is this paramagnetic or diamagnetic? It's diamagnetic because they're all paired up 2 by 2 by 2. We got, giraffes and mice and tigers and lions. I don't know. Okay. So we've talked about the size of atoms. Now we'll talk about the size of ions. So cations are much smaller than neutral atoms, and thankfully this makes sense. Because how do you make a cation? You take electrons off. When you peel things off of something, it gets smaller, right? So we're taking off electrons, and we're generally losing the entire valence shell, so we're going down another layer. And what we find is that the ion is much smaller. It's like half the size or less than the atom. Because when you do this, you end up with a tremendous increase in effective nuclear charge. But cations are smaller, you're losing electrons, it makes sense. Anions are, I said larger, didn't I? Yeah. Cations are smaller. It makes sense because we're losing electrons, we're peeling things off, they're getting smaller. I was just getting ahead of myself. Anions are bigger. And that makes sense also because now you're adding electrons, right? We end up with a lower effective nuclear charge, and so the anions are larger, and they are much larger, about twice as large. So anion about twice as big as the atom, cation about twice as small. And then we can talk about isoelectronic ions. So iso means the same, electronic refers to electrons, so same electrons. So these are ions of different elements that have the same number of electrons. So here are 4 isoelectronic ions. So sulfur, when it gains 2 electrons, it has the electron configuration of argon. When chlorine gains 1 electron, it has the electron configuration of argon, right? When potassium loses an electron, same as argon. When calcium loses 2 electrons, same as argon. So these guys are gaining electrons. Do we think they're going to be bigger or smaller? Bigger. So we're expecting that these guys be bigger, and we're expecting that these guys be smaller, right? Because when you add electrons, it gets a lot bigger, and when you take electrons away, it gets a lot smaller. And if we look at the masses here, no, that's not the masses. The number of electrons now is the same. The number of protons is different. So for calcium has 20 protons. Sulfur only has 16. So this is a smaller charge attracting those electrons, and so we expect it to be bigger. This 2 minus is going to be bigger than the 1 minus, and the calcium 2 plus is going to be smaller. And these are the actual radii, 184, 181, 133, 99. So in a series, the one with the most protons will have the smallest radius. the positive ion with the biggest charge. So here it's asking us to choose the larger atom or ion from each pair. The first two, we don't even need to look at a periodic table. Here we've got an atom and the cation. How did it become a cation? Did it gain or lose electrons? It lost electrons, which would make it smaller, right? So then potassium is bigger. Here we have neutral atom and anion. How do you make an anion? Gain or lose electrons? Gain electrons. Is that going to make it bigger or smaller? Bigger. So the fluoride would be bigger. And then we've got calcium and chlorine. Maybe unlock that door. I didn't realize it was locked. Sorry, I didn't mean to lock you out. Here's calcium, and here's chlorine. So when chlorine becomes an ion, it takes on argon's electron configuration. And when calcium becomes an ion, it also takes on argon's electron configuration. Right? So cations are smaller, anions are bigger. Which do we expect to be larger? The anion, the chloride. Okay? There's also a trend in ionization energy. Ionization energy is the amount of energy needed to remove an electron from an atom or an ion in the gas state. This is always going to be positive. You always have to pay the atom to take electrons away from it, okay? It's not just, they don't fall off, right? You have to pull them off. So we can write an equation for this. We can say, well, here's our metal in the gas state, and we put in some energy, and we get the ion, and we pull an electron off. So that's called the first ionization energy, removing the first electron. From that ion, you can put in more energy and remove a second electron. So that's called the second ionization energy. And then you could do that again. You could take that 2+ ion, put energy in, and pull off a third electron, and that would be the third ionization energy. What is that, 9, 4, 6, 4, 7? Looks like 47 on that clock. So there's a trend here. The first ionization energy decreases as we go down a group. So here are the noble gases, helium to xenon, and the ionization energy gets smaller. Here are the alkali metals. The change is not as big, but it's getting smaller as we go down. Well, why is this? Well, as you go down a group, the atoms are getting larger, right? So those electrons you're pulling off are the valence electrons, and the force of attraction depends on how far they are from the nucleus. So in a bigger atom, the electrons are further from the nucleus, it's easier to pull them off. And this is why, I quit going to the big Fresno Fair, once we passed up having 2 children, because that's the number of hands I had. And it just seemed like a great place to lose children. And I wouldn't do that on purpose. So, big family, little family. Who's it easier to snatch a kid from? Big family. You can't physically hold on to all of them, right? So, these smaller atoms, it's harder to take the electron from them, so the ionization energy is larger. If we're looking across a period, we see that generally, like going from lithium to neon, generally it increases. There are some zigzags in here, but generally it increases because for the same reason, the atoms are getting smaller because the effective nuclear charge is greater, right? So ionization energy increases. So ionization energy increases as you go across, and it decreases as you go down. And so this is directly related to the size, right? This is increasing size. And going across here is decreasing size. So they go together. So try to remember the size one. And then if you're looking at ionization energy, you can pick out, well, which one of these is bigger? And is it easier to snatch a child from Mrs. K when she had a small family or a big family? Right? Big family. I haven't lost any of them yet. Not for more than a couple hours. So on the basis of trends, determine which has the higher first ionization energy. So tin or iodine. Those sound familiar? So which one is smaller? Well, as we go across, they get smaller. So we expect iodine to be harder to take an electron from. Calcium or strontium? There's calcium and strontium. As we're going down, they're getting bigger, and it's easier. So the smaller one would be harder. Carbon or phosphorus? So here's carbon, and here's phosphorus. Well, this is going across would be getting smaller and having higher ionization energy. Going down is getting larger and having, going across is getting smaller, larger ionization energy. Going down is getting bigger, smaller ionization energy. Those trends are conflicting, they're opposing. And so again, it says if possible, and so we can answer not possible. And then fluorine or sulfur. This is getting very messy. There's fluorine and sulfur. Now, those two are also on the diagonal, but here, both of the trends reinforce each other. So going across, we predict fluorine to be smaller, to have higher ionization energy. Going down, we predict fluorine to be smaller and to have higher ionization energy. So we expect that fluorine is going to have the higher ionization energy. Any questions? The trend thing, it's not a really big deal, but there are questions on the exams about it. And it does come up in Chem 1B. So, of course, every trend needs an exception. So we just finished saying that ionization energy generally increases from left to right across a period because the atoms are getting smaller. But there's an exception between groups 2A and 3A. So draw orbital diagrams for bromine and beryllium. So boron. So boron has 3 valence electrons, right? And beryllium has 2. So this is boron, and that's beryllium. Boron has 3, and beryllium has 2. So let's look at what electron are we removing. Well, when we're removing an electron from boron, we're taking an electron from the 2p room. This room, this sublevel, is higher in energy than the 2s. Over here, we're taking from the 2s, and this is lower in energy. So this one is easier to remove than this one. Does that make sense? we would expect that boron would have a higher ionization energy because it's to the right, therefore it should be a little smaller. But it actually has a lower ionization energy because this is in a more expensive room and it's easier to kick this guy out than to take this guy out of the cheaper room, the lower energy sublevel. There's another exception between group 5A and 6A. So nitrogen, group 5A, oxygen, group 6A. So as we're taking off an electron, from nitrogen, we're going to take off an electron that has its own bed in this P room. And down here, we're going to take off one that's having to share. So this is easier to remove than that one. Like, well, how do we get the hotel analogy in here? It's like, well, we got to pay these people to give up their room, right? So this guy's going to give it up for less than that one. Because this guy's pretty comfortable. He's got his own bed. This guy's got to share. And so, yeah, give me money. I'll go find another place. Any questions? Yeah. So as we take off electrons, the first electron costs energy, the second electron costs more energy, the third electron is more, the fourth is even more, right? It's like, okay, well, I'll let you have the first kid for $50, but you want another one? No, we're up in the price now, and I'm running out of children, and so the price goes up and up, right? So here's sodium. Has a first ionization of 496. There's magnesium, first ionization energy of 738. We see that magnesium is to the right of sodium, and so as we go across, we expect that ionization energy to be larger. I'm going to look at what's happening here. So this is sodium, and this is magnesium. Magnesium has 2 valence electrons, and sodium has 1. So we take off sodium's 1 valence electron. That's this one here. So we remove that. Oops. That's better. And then the next one that we're going to remove, now that's down the next level, right? We just took off a 3s electron. Now we're going to go down to a lower floor to the 2p. Those guys are a lot closer to the nucleus. They're held more strongly. So we see this huge jump because we've gone through all the valence electrons, and now we're getting into the core electrons. For magnesium, we get rid of 1 electron. And it requires a certain amount of energy. And we get rid of the second electron. And it's more, it's like twice as much. But it's not this huge jump like for sodium. Because we're still picking off valence electrons. After we've lost 2, though, now we're down into the core electrons, and so the next one goes way up. Does that make any sense at all? Well, I told you about it. So here we see where that big jump is. So for sodium, after you take off 1 electron, it's 1 valence electron. For magnesium, you take off 2 valence electrons, and then there's a big jump. Aluminum has 3 valence electrons. You move the 3, and then there's a huge jump. Silicon has 4. After you've removed 4, there's a big jump. 5, 6, 7, right? So you remove the valence electrons. Each one is going to cost more than the previous, but once you get through the valence electrons, the price goes way up. Okay? Onion layers.